Hey guys, welcome to AI Tech Talks with Carl. Today we're going to be going over the gradient boosting classification algorithm from scratch in Python without using the SKLearn library in Python at all. So I highly recommend watching the previous video on gradient boosting regression because with the gradient boosting regressor algorithm, because this video is a follow-up to the regression algorithm I implemented before. And so it's a little more advanced than, as you know, than the gradient boosting regression algorithm. So I'm going to be going over pretty much every new line of code that I write in this video. And so the main resource I use for this video on gradient boosting classification is the Elements of Statistical Learning by Trevor Hasty and Jerome Friedman. This book is actually considered to be the Bible of machine learning by many, and it goes into great detail on statistical learning. And so the chapter that we're interested in is the boosting and additive trees. This goes over basically gradient boosting regression and gradient boosting classification and AdaBoost, and really explains it well. The next resource is the SKLearn library and specifically the gradient boosting classifier class in this library. And I basically implemented it the same as this third-party library, so we know it's the correct implementation of the algorithm. And so the library actually has in a lot of their citations the same book, the Elements of Statistical Programming book that I was describing before. So we first start with importing the necessary libraries for gradient boosting classification algorithm, including NumPy and GraphViz library. The only new function from the regression video, the previous regression video, is the xbit function from the scipy.special module. And this function is just a logistic regression function used to convert the log odds prediction into the probability predictions. And next, we are going to make a data set that is given in equation 10.2 in the Elements of Statistical Learning textbook. And this data set is described on page 339 of the book. So we set the random seed by passing a random seed parameter to the function and then set the features to a random normal distribution with the number of features equal to 10. And so we can see this on page 339 of the textbook with the standard independent Gaussian and the label as 1 if the sum of each feature in a training example is greater than 1 and -1 if not. So we implement the label with y here and set that equal to 0 or 1 with Boolean indexing. Then with NumPy advanced indexing, we change the labels with 0 to -1 as in the equation in type 10.2 in the textbook. Now we can call this function with the number of samples equal to default value and a random seed of 0 to get reproducible results. We can then divide the training and test data into 2,000 training points and 10,000 testing points, respectively. This is then the same example given in scikit-learn library and the simulation example from the textbook. The node and the decision tree regressor class will stay exactly the same because we are fitting each tree to the residuals, and thus it is a regression task. However, I did add another argument to the make prediction method where I pass the index of each node as I. The make prediction method now takes a single training example and the root node of the tree and returns a tuple consisting of the mean value of the leaf node it ends up in and the index of that leaf node. So if you don't know how binary trees are represented in array format, I put a link in the description below for your reference. Now I added the apply method after the predict method, and that basically makes predictions for each observation, but instead of returning the mean value of the leaves, it returns the index that the observation falls in. So the next thing that we have to do is create a class to implement the binomial deviance loss function used for classification. This is essentially the same loss function as the binary cross entropy and used to derive the equations for updating the output values of the leaves. So since the regression tests, the regression trees are derived from the probability predictions and not the log odds predictions, we have to transform the leaf nodes to the log odds prediction values. And so Josh derives that formula in part 4 of the series, and I implement that formula in the update terminal regions method described in the code. So in this method, I use pre-order traversal to first check if there are values in the node, which means it is a leaf node. If not, it is a decision node, and I call the recursive function again on the left and right nodes to traverse through the tree. When it lands on a leaf node and there is a values key in the info dictionary, then I set those values to the residuals and grab the observations that ended up in that leaf node. I used Boolean indexing to find those values by setting the indices returned by the apply method equal to the current leaf index. Then the equation is applied to update the leaf value with the numerator as the sum of the residuals and the denominator as the sum of the previous probabilities over the probabilities times 1 minus the probabilities. Then I clip the denominators so there is no zero division and return nothing. The get init raw predictions method below just gets the initial predictions for the first tree. I use the numpy bin count function to essentially create an array with the number of zeros in index 0 and the number of ones in index 1. This gives the counts of the number of training examples in the first class and second class. I use NumPy broadcasting to set a probability matrix with the first column as the frequency of the first class and the second column as the frequency of the second class. Then we take the elements of the second column, so basically the probabilities of class 1 occurring. Finally, I take the log odds of this probability with the logit function here and return the raw predictions for each observation in the training set. And this is actually the same method that Josh uses in StatQuest, where he takes the log odds value of class 1 or the Loves Troll 2 class. After the loss function is implemented, we can go down to the gradient boost classifier class. This class is generally the same as before, except we change the fit method a bit and add a predict proba method to calculate probability predictions. When we call the fit method, we pass the features x and the labels y to the function call. Then we define an instance variable to hold all the trees used for the stage-wise additive modeling. Since the simulated example has class labels of -1 and 1, we have to convert those to class labels of 0 and 1 by using the unique function in NumPy and setting the return inverse parameter to true. The return inverse parameter in the unique function is able to return the indices of the unique labels that were returned. So here it says if true, also return the indices of the unique array that can be reconstructed, that can be used to reconstruct R. So if we go to the example provided, we can see that the unique function returned 2 parameters. The U variable holds the unique values and the indices variable holds the indices of those unique values to reconstruct the original array with NumPy fancy indexing. So our U variable is going to be the classes -1 and 1, and the indices are going to be the original array, but converted to elements 0 and 1. Now we pass these converted class labels, or Y, into the binomial deviance init method and set the object to self.loss. Then we get the initial residuals by subtracting the probability predictions from the initial labels. We can then start the loop to build the decision trees and fit each tree with the feature matrix X and the residuals from the previous iteration. After fitting the tree, we have to update the terminal regions as in the StatQuest video by passing the root of the tree and the residual from the apply method, which returns the node label for each of the training examples in X. So we can append the tree to the trees list and calculate the current residuals for the next iteration after this. And then now to implement the predict proba method, which takes in the feature matrix X and starts by initializing an array of zeros to hold the log odds prediction for each training example and for each tree. Then we add the initial log odds prediction to the 0th column by calling the getInit raw predictions method of the binomial deviance loss class. We iterate through all of the updated trees and save the log odds predictions in the raw predictions array. Then we sum the raw predictions for the additive model and return the probability predictions with the xbit function from SciPy. And the predict method after this just gets the probabilities from this predict proba method and gets the actual class labels from the self.classes variable. Wow, that was a lot of work. Now all we have to do is initialize the gradient boost classifier object and fit the model with the training set. We will set the number of trees equal to 100 and the max depth to 3. Then we will call the predict method and make predictions on the test set. We print the accuracy by taking the sum of the Boolean array and dividing the number of test examples. This will take about 5 minutes to run because we are fitting 100 trees and updating the terminal regions. So it finished running, and you can see that we get decent results with a classification accuracy of 88% for the test set. As before, we are going to save the first 5 trees to a GIF with the GraphViz module that SKLearn uses. When I run this, we see a nice GIF of the first prediction and the residuals being fit in the decision tree. So that was it, guys. If you enjoyed the video, please like it and subscribe to the channel.